Hello everyone, in this video we're going to talk about Faraday's law of induction. This is a very important concept in electromagnetism and also one of the bases for the electric generators. So watch the video and you understand some of the Faraday's experiments and calculations. It was known that an electric field could induce a magnetic field. If we connect a battery to a coil like this, we can induce a magnetic field here just by the electric field of the battery. So Faraday, he was trying to prove the opposite, that a magnetic field could induce an electric field. So he tried and made some experiments. The first one, he took a magnet and a coil connected to a galvanometer to see if there was an induced electric field over here because of the magnetic field of the magnet. But when he put them close together, nothing happened. He then moved the magnet away from the coil and he noticed a small peak in the current. It was weird. So then he tried to move the magnet closer to the coil. And again, he noticed another peak in the current over here, but in the opposite way. He was kind of thinking about it and tried to make some more experiments. So for his next experiment, he tried to do something similar to the first one, but instead of a magnet, he was inducing a magnetic field through this electric field of the battery over here. So it was basically a battery connected to a coil that was coiled around this magnetic core, and on the other side we had another coil connected to a galvanometer. So if it was true that a magnetic field could induce an electric field, the magnetic field over this side of the coil over here could induce an electric field to the onto this other coil over here, and he could measure with the galvanometer. So here was the setup of the experiment. Then he turned the switch on to produce a magnetic field over here, and he noticed a peak in the current again. So it went to 10 and went back to 0. And when he turned off the switch, again another peak in the current, but in the opposite direction. So he started to think what was happening here. Why does the current go to 10, for example, and went back to 0? It was clear that this magnetic field could induce an electric field, but it was not constant, right? What was happening? So this is exactly what was happening there. When he turned on or turned off the switch, the magnetic field starts to increase until it's constant. And when he took the battery off, turned the switch off, the same thing happened. It was in a maximum magnetic field and it started to decrease the magnetic field. So what was causing an electric field over here, the induced electric field, is actually proportional to the change in the magnetic field. It's not only the magnetic field itself, but the change, alright? So the magnetic flux that passes through this other coil here that produces electricity. So EMF, electromotive force, is induced by a changing magnetic field, okay? Not only the magnetic field itself, but a changing in it. So let's go now through the Faraday's law of induction. So we've seen that the electromotive force, or the induced voltage, is proportional to the number of loops in the coil and the change in the magnetic flux over time. All right. So this is exactly what produces electricity. Another way to think about that experiment is, instead of a magnet like this, you can build something that looks like this. So we have the magnetic poles over here, and right in the middle we have a coil, but instead of doing a lot of loops through this coil or moving further away the coil from the magnet, what we can do, we can just turn this coil over here inside the magnet. Okay, you can rotate this coil over here to produce a change in the magnetic flux, and then an induced voltage. Alright, so for a case like this change in the magnetic flux would be the change in the magnetic field strength inside here times the area of the coil over here times the cosine of the angle perpendicular to this area. So because you're rotating this coil, this area is constantly changing, and the magnetic field strength that passes through the coil is also changing. And this change produces a change in the magnetic flux, and this induces a change in the electric flux, electric field. Okay, we have an induced voltage. This is the principle of the electric generators. Alright, now it's time to practice a little bit of the concepts and formulas we've learned. Alright, we have an EMF that's induced by a rotating coil that has 1,000 turns and it's 20 centimeters diameter. Alright, and it is in the Earth's magnetic field that's 5 times 10 to the negative 5 Teslas. We want to know the average EMF that's induced, given that the plane of the coil is originally perpendicular to the Earth's field and is rotated to be parallel to the field in 10 milliseconds. So let's think about this problem a little bit, right? We can use our formula for Faraday's law, alright? But before this, we want to know the change in the magnetic flux, right? So this change is proportional to the magnetic field. In this case, is the Earth's magnetic field. Also the area of the coil and the cosine of the angle, okay? Because we're rotating this coil over here. Okay, so we can calculate this difference in this change in the magnetic field flux. First, let's calculate for the first moment, alright? So we have that when the coil is originally perpendicular to Earth's field, the angle would be 0, and cosine of 0 is 1. So initially, the magnetic flux would be simply the magnetic field strength times the area of the coil, right? Now, for the second moment, when the coil is parallel to the field, we have that the cosine, that the angle is 90 degrees, is parallel, right? So the cosine of 90 is 0, so everything here is 0. So the magnetic field flux in the second moment after 10 milliseconds is 0. Okay, good. So the change in the magnetic flux would be this first moment minus, the second moment minus the first moment. And it would be negative minus, the magnetic field strength times the area of the coil. Now we can go back to the Faraday's law, alright? First, of course, let's calculate this this change in the magnetic field flux, okay? We have the values here for B and for A. We are considering this is a circular coil, okay? So the arrow is pi over 4 times the diameter squared, okay? So the change in the magnetic field flux is negative 1.57 times 10 to the negative 6 Tesla meter squared. Alright, very good. Now let's go back to the Faraday's law of induction, and we have all the numbers also. We have that's a 1000 turn coil, okay? We have the change in the magnetic field flux, and we have the change in time. It goes from perpendicular to parallel in 10 milliseconds, okay? So we have that the average EMF that's induced by this situation here is 0.157 volts or 157 millivolts. So that's it for today. Hope you enjoyed and see you next time.